Hello, everyone. My name is Pan Zhao. I'm currently a postdoctoral research in the Department of Mechanical Science and Engineering at the University of Illinois at Urbana-Champaign. It's my great pleasure to have this opportunity to present our recent work on intelligent crop management via deep reinforcement learning and crop simulations. This is a joint work with my colleagues Ran Tao, Jing Wu, and my collaborators Nicholas Martin and Naira Hovakimian. Modern agriculture is facing significant challenges in order to close the significant gap between the amount of food produced today and that needed by mid-century. This challenge was further magnified by a few other problems such as soil degradation, climate change, and water scarcity. For instance, in the last 150 years, half of the topsoil on the planet has been lost. The world urgently needs to move towards more sustainable agriculture systems. Among different factors, crop management is a key controllable one, influencing crop production, resource usage, and environmental impact. Therefore, optimized crop management is essential for sustainable agriculture. However, there are many management practices involved that are related to, for example, fertilization, irrigation, tillage, and cover crops, so on and so forth. And it is quite challenging to find the optimal management practices to improve crop productivity while minimize the resource usage and environmental impact. So here's our vision for this problem. So crop management is essentially a sequential decision-making problem because a few decisions need to be made sequentially across a period. For example, when and how much to fertilize. Reinforcement learning has achieved superhuman or remarkable performance in the last few years on various sequential decision-making tasks, for example, in board games, video games, and robotic control. And we believe that reinforcement learning, or RL, has great potential for optimizing crop management. So here we show our Envisioned framework for intelligent crop management via RL. So during policy training stage, we let RL agent interact with virtual cropping system simulated by a crop simulator. We then apply deep reinforcement learning algorithms to train the management policies. And when deploying the trained policy in the real world, we use some sensors to measure the weather, crop, and soil conditions, and then apply the management practices, for example, related to fertilization, irrigation, and tillage following the trained policy. So now let's discuss the role of crop simulators. First, why do we need crop simulators? The reason is training a management policy using deep RL may need millions of interactions between the RL agent and the cropping system, which is just infeasible for field experiments. Therefore, this using crop simulators is the only feasible solution. Second question is, what are the requirements for the crop simulators? And from our perspective, there are two key requirements. The first one is that the simulator should have a relatively good fidelity, and it's widely used by researchers. For this, we have a few options such as AppSim, DSAT, that can satisfy this requirement. And the second requirement is that this simulator should be able to interact with our agent on a daily basis. in light of these two requirements, we eventually choose DASAT and leverage the Steam DASAT to enable the simulated cropping system to interact with our RL agent on a daily basis. In order to apply the RL algorithms, we first needed to formulate the crop management as a Markov decision process or MDP problem. And this involves the determination of the state space, action space, and the reward function. And here our state space includes a few state variables to characterize the crop status, for example, growing stage, weight, and to characterize the weather conditions such as rainfall, temperature, and as well as soil conditions, for example, water content and organic matter. And the action spaces will include the variables to determine fertilization, irrigation, tillage, residual retention, cover crops, and so on and so forth. Finally, our reward function will depend on our optimization objectives. For example, if we wanted to maximize crop yield as well as the stored organic carbon in the soils, we may choose a reward function like this one that rewards the stored carbon and the yield while penalizing higher nitrogen leaching and higher management cost. And with the MDP problem, we can now apply the steeper RL algorithm to train the management practices, train the management policies. So here we show how the training is performed using Deep Q network or DQN. The interaction between the agent and the simulated environment will generate data in the form of tubes of the current state S, current action A, reward R, and next state S prime. And these tubes will be stored in a replay buffer. And then with a certain frequency, some tubes will be sampled from this buffer and used to update the Q value function represented by a new network by minimizing a loss function. And such Q value function can be used to determine the optimal action given a state. Additionally, during the training, we can also incorporate the so-called domain randomization by randomizing the weather during the training to improve the robustness of the training policies against uncertain weather conditions. Next, we show a case study for nitrogen management. The results I'm going to present is from the paper, our paper that has been recently accepted by this workshop. And more details will be included in the poster presentation given by my colleague. So for this study, we consider the corn in Ames in Iowa State of the United States. Our reward function depends on the yield, nitrogen leaching, and nitrogen input. Our action spaces include 5 possible amounts for the nitrogen fertilizer for each day. And we set the irrigation to 0 to be consistent with the practices in Iowa. And our state spaces include 37 states output by DSAT, which further consists of variables to characterize the weather, such as temperature, rainfall, and soil conditions, such as water content and nitrogen leaching, and variables to characterize the crop, like a growth stage, plant nitrogen and water stress, top weight, and so on and so forth. And we use DQN RL algorithm, where this Q function is approximated by a network of one hidden layer with 256 nodes. So here we show the training curve of cumulative reward versus episodes. And the right figure just a zoom in figure of the left figure. And the training curve is averaged over 5 trials. So we could see that the policy consistent convergence with roughly 800 episodes. We next show the performance of the trained policy in comparison with some baseline policies, which apply the fertilizers when the plant has 5 expanded leaves, according to existing literature. And the evaluation criteria includes the total nitrogen U-boat, total nitrogen leaching, yield, and cumulative reward. We could see that compared with the baseline, the RL policy actually leads to more yield and roughly the same leaching, while with the same or smaller amount of fertilizers. Also, by looking at the trained policy, the nitrogen application history, we could see that the trained policy represented by this red bars uses a quite a different strategy in applying the fertilizers compared to the baseline represented by this blue bar. So we can see that the trained policy tends to apply the fertilizer multiple times at different growth stages. Next, we show a recent case study for the joint nitrogen and irrigation management. For this study, we consider the corn in Florida of the United States. Our reward function depends on the yield, nitrogen input, water input, nitrogen leaching. And our action space includes 5 possible actions for fertilizer, as well as 5 possible actions for irrigation. Our state space is similar to that used in the previous study on nitrogen management. Again, we use DQA, and we use 3 heating layers, a neural network of 3 heating layers to approximate the Q function. Here we show the training curve of cumulative reward versus episodes. Again, averaged over 5 trials. So we could see once the policy consistently converges with roughly 3,000 episodes. So here we show the performance of the trained policy in comparison with baseline policies, which apply the fertilizer and water following a production guide for the Florida corns. We created 3 baselines, which corresponds to different water amounts, as the production guide actually just tells how much water are needed, but it didn't tell how much water should be applied through irrigation, because the total amount of water applied to the crop also depends on the rainfall. So we could see that the trained policy actually achieves much higher reward and yield while using fewer fertilizers and less water. And by looking at the fertilizer and water application history, here we also show their history. So the trained policy is shown by the orange bars, and the baseline policy are shown by the green bars. We can see that the trained policy chooses actually quite a different strategies compared to baseline. So for instance, the baseline policy is trying to irrigate evenly with a certain frequency, while the trained policy irrigate intensively here at certain stages, here. and does not aggregate at all in some other stages, for example, this area. To summarize, we have presented a crop management framework based on deep reinforcement learning and crop simulations. We obtained quite promising results for nitrogen and irrigation management for crops in Florida and Iowa. Our results demonstrated the potential of deep RL and crop simulations in optimizing crop management for sustainable agriculture. There are also a few exciting directions to explore next. First, we would like to develop the interface for AppSim to facilitate its use in training and evaluating management practices. This is because AppSim is equally, if not more, widely used compared to DSAT. Moreover, AppSim has been well calibrated for the US Corn Belt. Also, we would like to incorporate soil carbon sequestration as an additional objective. As we may know, soil is the second largest carbon pool on the planet. But modern farming practices have caused the depletion of the soil organic carbon pool by 60% to 75%. And this loss of soil organic carbon is the major source of soil degradation. And according to the United Food and Agriculture Organization of the United Nations, that we may have less than 60 years of farming left if soil degradation continues. And in light of this soil degradation crisis, Save Soil global movement has been launched this year to raise people's awareness about soil degradation and promote the national policies to help restore soil health. And as part of this movement, there will be Save Soil walkathon in over 60 cities across North and Latin America this June. And actually, all the walkathon in the United States happen right this weekend during the Saturday and Sunday. Finally, we would like to bridge the sim-to-real gap, which is a well-recognized problem in reinforcement learning. The potential ways include the domain randomization, where we basically will randomize the some simulation parameters to make the policy robust against the model mismatch. Another way is based on the cross-simulator validation. So for instance, we could first train a policy using AppSim and then validate this policy using DSAT. Finally, I would like to thank again my collaborators and also C3AI Digital Transformation Institute for sponsoring our work. With that, I would like to conclude my talk, and thank you very much for your attention.